Electronegativity and permanent dipole, A-level chemistry. Bond polarity and electronegativity. Electronegativity is a term we only use in case of covalent bonding. So the electronegativity is the atom's ability to attract the bonding electron pair in the covalent bond. So there is the electronegativity of different elements is measured on a scale where each atom has a certain electronegativity or ability to attract the bonding electron pair. The higher the value, the more electronegative the element. So we can see here fluorine has electronegativity of 4 and hydrogen, for example, has an electronegativity of 2.2. So there is a difference in electronegativity and fluorine will have more ability to attract the bonded electron pair if it's bonded to hydrogen. The electron pair in a covalent bond are not evenly shared between the two atoms if they have difference in electronegativity. So we can see here in the case of hydrogen fluoride, well, fluorine is more electronegative than hydrogen, so it attracts more of the electron pair or has ability to attract the bonded electron pair towards itself. So there is more of the negative charge cloud towards the fluorine than it is around the hydrogen. That means that the bond between the two atoms will be polarized in this case. There will be a partial positive charge on one atom. In this case, this is going to be on the hydrogen, a partial positive charge, and there will be a partial negative charge on the other atom, which has a higher electronegativity. The greater the difference in electronegativity between the two atoms, the greater the polarizability of the bond. So the bond between the hydrogen and fluoride will be more polarized than the bond between hydrogen and oxygen because the difference in electronegativity between hydrogen and oxygen is less than the difference between hydrogen and fluoride. So we know that electronegativity now is the ability of the atom to attract the bonding electron pair in covalent bond. So this power will depend on two main factors. The first one is the size of the atom, because the size of the atom means shielding. So the bigger the size of the atom, that means that the bonded pair will be further away from the positively charged atom and a positively charged nucleus and will be shielded with the inner shell electrons. So the bigger the size, that means that the electronegativity will be less. And also the nuclear charge. So the higher the nuclear charge means that the power of the positively charged nucleus to attract the bonded pair will be higher. This is why across the periodic table we can see that across the period the electronegativity increases as you go right. This is because the nuclear charge increases. Remember that electronegativity is the term we use only with nonmetals which do or take part in formation of covalent bonding. We are not talking about metals here. And along the group, electronegativity will decrease. As you go down, this is because the increase in the shielding. So across group 7, for example, you can see that fluorine will have higher electronegativity than chlorine, which will have higher electronegativity than bromine, and so on. So when we see now that electronegativity increases across the period, decreases across along the group, that means that fluorine will be the most electronegative element in the periodic table. Permanent dipole. So due to the difference in the electronegativity between the bonded atoms in case of covalent bonding, the bond will be polar, and we call it to have, or we say that it has a permanent dipole. So again, when we look at the bond between hydrogen and fluorine, we can see that fluorine is more electronegative. It attracts or has the power to attract or pull the electron pairs towards itself more than the hydrogen, and that creates a positive partial positive charge around the fluorine and a partial negative charge around the hydrogen. So this is hydrogen-fluorine bond, and we can say that this is the dipole. We represent it with this arrow going toward the where the negative charge goes, and then we have a positive, partially negative charge on the fluorine and partial positive charge on the hydrogen. We give the partial represent the partial positive and a partial negative with the delta symbol. Polar and non-polar molecule. So we know that a permanent dipole will only be seen if there is difference in the electronegativity between the covalently bonded atoms. So normally if the covalent bond is formed between two atoms that have the same electronegativity or similar electronegativity, the bond will not be polar. We can see that in case of the diatomic elements like oxygen or hydrogen. We can also see it in the bond between the carbon atoms and hydrocarbons in case of organic compounds, or also between carbon and hydrogen, because the difference in the electronegativity between carbon and hydrogen is very small, so it's almost considered to be there is no difference or there is very similar electronegativity, so the bond between carbon and hydrogen are not polar. This is why hydrocarbons as organic molecules are non-polar, because all the bonds are non-polar. You would expect that the molecule, any molecule that has polar bonds, to be polar as a molecule. However, polar molecules which have a dipole moment or have polar bonds can either be polar or non-polar. Polar molecules will have an even distribution of the charge across the whole molecule. Like hydrogen fluoride we have seen. So in case of hydrogen fluoride, you can see that there is an even distribution of the charge across the whole molecule, where more of the negative charge towards the fluorine and the positive charge towards the hydrogen. We can also see it in case of water molecule. There are two polar bonds in water, and there is an even distribution of the charge across the whole molecule, so the whole molecule has a permanent dipole. However, nonpolar molecules, the polar bonds are in this case arranged symmetrically in the molecule, so there is even distribution of the charge across the whole molecule, and the charges will cancel out, so the molecule has no permanent dipole. We can see that in case of something like carbon dioxide. So the bond between the carbon and oxygen is polar bond. There are two different polar bonds in this molecule. However, the bond dipoles work in opposite direction, as we can see here, and there is an even distribution of the charge across the whole molecule. So the molecule has no dipole moment. You can see also this difference in case of something like carbon tetrachloride and trichloromethane. In case of carbon tetrachloride or tetrachloromethane, the molecule here is symmetric. The distribution of the dipole moments or the charge is symmetric. The molecule has a tetrahedral shape, so the molecule is nonpolar. However, when you have only three carbon-chlorine bonds which are polar and then one carbon-hydrogen bond here, then the molecule will be polar because there will be uneven distribution of the charge across the whole molecule. So this is going to be a polar molecule.